Here we have a system of three equations in three variables. And typically solving a system like this, you would want to use the addition method, also sometimes called the elimination method. Up to this point, we've only normally done it with two equations and two variables. So let's see how it works when you have three. So first of all, what you want to do is look at the coefficients in each of the variables. So the coefficients of x are 5, 3, and 6. In the y column, we have coefficients of 3, -4, and -5. And in the z column, we have -5, 3, and 6. First thing you want to notice is there a column where the numbers are particularly compatible? And by that I mean they have a low common multiple. The other thing you want to look for, though, is similarities. And in this case, 5, 3, and 6 appear both in the x's and the z's. So my first thought would be to focus on eliminating one of those variables. The other thing that I've noticed is that in the x's, 3 and 6 appear in both equations 2 and 3 in front of z with the same signs. So if you eliminate x, you're also going to eliminate z. Let's see how that's going to work. So we want to figure out how to do that. Well, we're going to have to multiply equation 2 by -2. Let's see why that works. I'm going to document it like this. -2 times equation 2. It's always good to document your steps so that later on when you go back to check, then you can figure out what you were up to. So -2 times everything in equation 2 would give me -6x plus 8y minus 6z equals 80. I'm just going to keep equation 3 the same. 6x minus 5y plus 6z equals -68. It's worth the effort to recopy it because with the addition method, you want to have them lined up so that you can now add and see what happens. When you add vertically, -6x plus 6x cancels, and that's gone. 8y minus 5y is 3y, but also in the z column, -6z plus 6z all cancels. And that's why you look ahead and decide what you're going to eliminate based on what you can see will happen. When you add the constants, you get 80 minus 68, which is 12. 3y equals 12, and simple to solve for y, divide both sides by 3. You've already solved for one variable, y equals 4. That doesn't always happen, but again, we planned ahead, and that's why it did. Now, the next step, of course, is we want to still solve for the other two variables, x and z. But since we already have one of them, which is y, we should plug it in for y in two of the equations. Now, we've already used equations 2 and 3 for this part of the process, so you want to pick a different pair for the next step. So I'm going to pick equations 1 and 2 this time. I'm going to recopy them, but except for everywhere that I see a y, I'm going to replace it with the number 4. What will that look like? Turn the page. In the interest of time, here's equations 1 and 2 copied over, except for they have 4 in place of y. What will happen now is we can simplify these quite a bit. So in the first one, 5x plus 12 minus 5z equals 12. And we're trying to get these into standard form, so anytime you have like a constant number, like plus 12, you don't want to have it over here with the variables, so let's get rid of it by subtracting 12 from both sides. And that will give me 5x plus, that's gone, sorry, not plus, minus 5z equals 0. And then in the second equation, 3x minus 16 plus 3z equals -40. So this time let's add 16 to both sides so that we get 3x plus 3z equals -24. How did I know to do that? Well, really my goal is to reduce this to a system of two equations in two variables. So now both of these equations only contain x and z, and I know how to solve a system with two equations and two variables from previously. I'm actually going to renumber these new ones. I'm going to call this one equation 4 and this one equation 5, just to keep my documentation nice and clean. All right, let me recopy those equations onto the next page. Here they are, nice and tidy. The last step, of course, is to solve for x or z as given. And we can see that neither one has much of an advantage, being the coefficients here are 5 and 3. Here they're negative 5 and 3. But at least these are opposite signs already. So I would choose to eliminate z by multiplying equation 4 by 3. And of course I'll document it like this. 3 times equation 4. That gives me 15x minus 15z equals 0. And then multiplying equation 5 by 5 to get 15x plus 15z equals negative 120. Be careful, because it's common to forget to multiply this side of the equation as well by the number. Add, addition method, right? 15x plus 15x is 30x. Z's are canceling, and I get 30x equals negative 120. Divide both sides by 30, and I get x equals negative 4. Remember from before I had y equals 4? Well, the very last step, of course, is just to get z. And you could choose any one of the equations from the original system to solve for z. So, for example, equation 1 was 5x plus 3y minus 5z equals 12. So if I put in what I know, 5 times negative 4 plus 3 times 4 minus 5z equals 12. And then 12. Negative 20 plus 12 minus 5z equals 12. What does that work out to? Negative 8 minus 5z equals 12. Add 8 to both sides. You get negative 5z equals 20. And then divide both sides by negative 5. And you get z equals negative 4. Typically, for a problem like this, you would write your final answer as what's called an ordered triple, meaning that all 3 answers need to be put in order of the alphabet. So x is negative 4, y is 4, and z is negative 4. And then you put parentheses around that, and that would be a way to write the solution that everyone can understand. Hope that helps. Have a great day.